Morning, everybody. There's a lot of positive energy today. What's going on? Is there a test coming up today, or did you just finish tests? Yeah? I always can tell when my students are taking tests in other classes because you're walking down the hallways. All right. Let's turn you into zombies some more by talking about the Bios of Arla. Oh, reminder that GRASP opens tomorrow at 8, not 7. I know some people like to come at 7. I will not be there tomorrow. I'm getting shots in my back instead. And Dr. Kerfoot will be opening the door at 8. The tutors will be there. You'll be in good hands. We left off last time having been through the horror that is the Bios of Arla, right? And finally got to a punchline, right? This thing here in the box. This is definitely something you want in your toolbox for this chapter, right? Because it gives us the magnetic field, right? For a well, in this case, an infinite wire, right? At any distance from the wire, we can find the magnetic field. So that's the magnitude. We need to talk about finding the direction of magnetic fields. We saw a video how the magnetic fields are circles. They form circles around the wire. This gets pretty difficult to draw, so bear with me here. I'm going to try to draw like a wire. This is sort of an isometric sort of thing, right? And the magnetic field lines will wrap around the wire, right? Kind of like that. They'll form these. I didn't do that right at all. Let's try again. Drop back here. Comes around, and it passes like behind. Oh, that one was bad. You see how hard this is to draw? Sort of. Okay. They're passing behind the wire there, right? And they form these concentric circles around the wire. And this wire has to have current flowing in it. So we'll say the current's flowing this way. And in that particular case, all of these fields would be rotating that way. So it's hard to draw the picture in 3 dimensions, right? And so we can sort of revert to our 2-dimensional pictures where like the current's flowing this way. I've kind of rotated this first picture right here and I've swung it around, right? Like that, and we're just looking at it edge on. And if the current's flowing that way and our field lines were sort of wrapping around this wire in this direction, that would mean that I've got magnetic field above this wire that points into the page and below the wire points out of the page. If I drew it so that the wire was looking at us and the current was coming out of the screen at us, then my magnetic field lines would look like that. Bless you. So all of these directions of this magnetic field and different ways of drawing it are dictated by the right-hand rule. But in this case, we don't have any, there's no cross products here, right? We started with a cross product, I'll give you that, right? There were cross products in the Bios of Arla. But as far as like this equation right here in the box, right? The magnetic field of surrounding this wire because it has current in it, that doesn't have a cross product in it. And so we're not going to use the handshake rule. We're going to use the hitchhiker rule that we kind of had for the magnetic moments, only we're going to change it around just slightly. Okay? So this is what I consider like the second major category of right-hand rules, these hitchhiker kinds, right? And what we're going to do is we're going to use our straight thumbs, kicked out like that, to point in the direction of the current. So what way is the current flowing here in this middle picture? Well, it's flowing to the left, right? So I would hold my hand, thumb outstretched, pointing to the left, following that straight current, and my fingers wrap around in the direction of the magnetic field. So as I take my fingers and I kind of wrap them like around and I try to go into the screen, which way are my fingers pointing? Into, right? Which is why above the wire I'm into, right? But as I come around the wire, around it and come to the bottom, which way are my fingers pointing? They're pointing outward, right? And if it helps, you can like grab your pencil, right? And pretend like it's the wire. And then you take your thumb and point in the direction of current. You wrap your fingers around the wire, right? So in the right-hand picture here, I've got my current coming out of the screen. My thumb is out of the screen, and my fingers are wrapping around in the counterclockwise direction, right? It's just that we got to remember that it forms a complete loop, right? It goes all the way around the wire. So all three of these diagrams are different depictions, different rotations of looking at the same thing. And our right-hand rule is straight thumb, right, for the current, and then our fingers will wrap around the wire in the direction that the magnetic field lines go. So where did I took it out. Okay, so let's do that. Let's do a problem where we're going to take advantage of our equation, right? We have an equation for the magnetic field of a current carrying wire and put it together, right, with the right-hand rule that I just taught you so that we can find total or net magnetic fields in space. So what have I got? I've got two wires, 10 amp current to the right, 20 amp current to the left on the bottom, and we are going to find the magnetic field at the three labeled points, A, B, and C. Now, of course, there's magnetic field everywhere around these wires, but we are going to just find it at these three places, and the distances are all given there. So we've done field additions before. Back when we did electric fields, we had 2 or 3 charges placed down, and we had to find the net field at a point in space. What was like our process? What did we take advantage of? Symmetries. A field is a vector thing, right? So if I can find the field from one charge and separately find the field from another charge because they're vectors, what can I do to find the total? Just add them together, right? Okay. So we're going to do the same thing, but magnetically, with magnetic fields, right? We're going to find, so like at point A, does point A have a magnetic field because of the 10 amp wire? Yes. Does it have a magnetic field because of the 20 amp wire? Yes. So we're going to find them separately at point A, and then we're going to put them together as vectors. This is the tried and true method. You've been doing it since Physics 4A. If you got vector things, find them separately and then add their influences together to get the total. All right, so in red at point A, right? We're going to have a magnetic field from the 10 amp wire. And let's see, what was my equation? It was mu naught times the current, all divided by 2 pi. I use the symbol A. You can use the symbol R. As long as you remember it's not the radius of the wire, it's the distance, right, from the wire. So that'll be the magnitude, right, for the 10 amp current. And then the magnitude for the 20 amp current is going to be the same equation, just different current and different distance, right? So let's go ahead and let's just calculate out these magnitudes, right? When you're using this equation, put the direction away for just a little bit, right? Concentrate on calculating out your number and start there. This is 4 pi times 10 to the minus 7 in SI units. It's a 10 amp current, all divided by 2 pi. And then what am I going to put in for the distance from the 10 amp wire to point A? Yeah, I'm not going to put in 10. I'm going to put 0.10. You could do 10 times 10 to the minus 2 if you wanted to, right? To get from, you got to convert it into meters because the constant is expecting meters Otherwise, it'll be weird. Okay, so let's see. What did I get? I did this in my calculator. I got 2 times 10 to the minus 5. And what would the unit be here? If I'm solving for magnetic field. Tesla. If I put standard units in, I don't need to keep track, right? As long as I put in meters and amps and all that, it'll come out in Teslas. Okay, down here, very similar. 4 pi times 10 to the minus 7 times 20 amps now, all 2 pi. Okay, what do we put in for the distance from the 20 amp wire? 0.3, right? It's 30 centimeters away. So it's going to be 0.3. And I can't tell you how badly I want to square that radius. But you don't, right? Don't do it. It's so tempting. Just don't do it. Okay, this turns out to be 1.33 times 10 to the minus 5 Tesla. And that's interesting. It is smaller, isn't it? It's a bigger current. It's got twice the current, but 3 times as far away, right? So distance seems to win there. Okay. Those are the values, right? Those are just the magnitudes of those two magnetic fields at point A. Now we need to satisfy direction. We need to go through and we need to figure out which way these things are pointed, right? So we're going to use our right-hand rule, and because this is a field, right, and forces are not involved here, it's not a hitchhiker. It's not a handshake, it's the hitchhiker, right? So which way are we going to put our thumbs for the 10 amp current? We're going to do it to the right, and then we really only need to concern ourselves with point A, right, which is above the 10 amp wire. So if we take our thumb and we put it there, we could wrap it all the way around if we wanted to, but we just come over the top. Which way are my fingers pointed? Out of the screen, right? So you can choose to do this any number of ways, but what I do is I say plus K hat for out of the screen. You can even say out, right? Which is out or plus K. I'd understand what you're saying. So if you take the 10 amp current, right, and you take your pencil, right, and hold it and pretend it's the wire. If you take your thumb and you point it to the right, you like wrap your hand around the pencil, right? Do you see how your fingers wrap around the top? If I was doing it from your point of view, right, I'd have my pencil, I have my fingers going like this, and I wrap my hand around my pencil. On the top of my pencil, which way are my fingers pointed? Out towards me, right? As they wrap around at the bottom, which way are they pointed? Inward, right?
No, but I'm saying no matter what, if it's wherever your thumb's pointing, that's where your thumb's.
Your thumb always points in the direction of the current. For now.
I know, but then we just follow the natural.
Yeah, and then it's the natural curvature of your fingers. Yeah. Again, no physical pain, just mental and emotional trauma. Okay, let's do the 20 amp current, right? What direction is the magnetic field from the 20 amp current at point A? It's going in, isn't it? Right? My hand is wrapping into the screen through point A. And so I would call that minus K hat or into the page, right? So to get the magnetic field at point A, what are we going to do? We're always adding 2 times 10 to the negative 5 plus 2 times 10 to the minus 5 plus K hat plus 1.33 times 10 to the minus 5 minus K hat, right? So this addition turns out to be subtraction, if you want to think of it that way, right? So in effect, I would subtract these two numbers, and I got 6.7 times 10 to the minus 6. Teslas. K hat. I should have done that the other way around. K hat Teslas. There we go. We don't cancel. If Lewis has 2 apples and Mr. Balogh has -1 apple, how many apples do they have? Just 1, right? He had 2 and I had -1. It's hard. And yeah, the number line is hard. What? I did 2 minus 1.33. What's 2 minus 1.33, Lewis? It's 0.67.
Yeah, I know that. But I'm saying, okay. I was just looking at the positive and the negative.
Yeah. What about them?
I just thought they canceled, but that's not. I don't know. It's okay.
They don't cancel.
No, I know they don't.
Okay, all right. We're good? We're good? No. Could be my bad too. All right, let's do point B. Is our approach going to be any different? No, okay? But we do need to make sure we get the right magnitudes. Will the magnitudes change? Okay, the magnitude from the 10 amp wire is going to be exactly the same. Why? It's exactly the same distance, right? So it's just 2 times 10 to the minus 5 Teslas. Have we changed the 10 amps? No. What's the distance? 0.10 centimeters, right? We subtracted. You guys are so smart. You guys are so smart. But sometimes you just have to be shown. What's 2 minus 1.33? 0.67, right? And then you move. We good? You're supposed to be able to handle scientific notation at this point. No? It's okay to forget. It is.
We're all post-exam.
Post-exam trauma. You know, it's funny. Just a tangent here a little bit, right? This would be 0.67 times 10 to the minus 5, right? Because these had 10 to the minus 5s on them. When you do scientific notation enough, you stop seeing those as being different. And that's probably where the rails went off, right? Because I didn't looked at it and it's the same to me. And that's my problem. Like I should have written it maybe like this instead, right? I should have put that together. No, it's like, you know, I have expertise in doing this a lot. You guys don't do it all the time, and so it can be. I can see how that can be confusing. It's just subtraction. Yeah. Subtraction's mean. It really is. Let's banish negative numbers. No, let's not do that. Okay. The thing I'd like to banish is algebra, but I need it too much. I'd much rather do differential equations for the rest of my life. All right. So is everybody okay? Are we okay? Is everybody okay that that's 2 times 10 to the minus 5? The magnitude is the same because the distance is the same, the current's the same from the 10 amp wire. But the 20 amp wire is a little bit different, right? It's going to be 4 pi times 10 to the minus 7 times 20. That doesn't change. All over 2 pi, that doesn't change. But what am I going to put in for the distance? 0.1, right? Because at point B, we're only this far away from the 20 amp wire. And when I did that, I got 4 times 10 to the minus 5? Okay, so we've got magnitudes, but now we need direction, right? So what direction does the magnetic field point from the top wire at point B? So I'm coming, my thumb, it wraps around my wire, coming out above the wire, but as I come below the wire where point B is, which way are my fingies pointed? Into the page.
Invading your space slowly.
We're not good again? No, Lewis, go ahead.
No, it was just okay. So the top one, right, was out, and now it's not out.
Right, because we were above the wire at point A. And now we're at point B, which is below the wire. Remember, it's a circle that goes all the way around. Yeah, so if it comes out at the top, it has to go in at the bottom. And if it goes out at the bottom, it has to go. Good. All right. And the 20 amp wire. Which way is the 20 amp wire's magnetic field pointed at point B? In. It's pointed into. My thumb is pointed to the left. My fingers are going into the screen. Like literally, if my thumb was in the plane of the screen, I have to my fingers have to go into the screen through point B. Yeah, where it's wrapping around, right? It has to wrap around and make a circle. So my fingers wrap around the wire, right? They wrap around my wire, giving me the direction of circulation. Pass through. End, I wouldn't say end. I'd say pass through. Yeah. Yeah. Right. Yeah. Continue the circle all the way around. Good job. I like that you guys are keeping me on my toes and demanding explanations. It's much better than being passive and just sitting there going, "What's happening?" All right. What are we going to do with these two numbers? We're going to add them together. We always add them. It's just that we actually add them this time, right? It's two negative things. They're both going in the same direction. So when I put them together, I get 6 times 10 to the minus 5 times a negative k hat. And what does the negative k hat mean? It's pointing into. Did I go too fast there?
Can you think of the K values as like negative or positive by themselves?
Yeah. Come on, dude. Yeah. They'd factor out and you just leave minus signs, whatever, doesn't matter. Are we good? He did it. I think he got there in the end. Okay, good. All right. At point C. Yeah, I did it.
Would you be okay if we wrote like positive k hat as like a vector, like 0, 0, 1?
Sure. And just make sure negative k hat 0, 0, minus 1. Yeah, I read vector in lots of different forms. All right. Do we have to recalculate the magnetic field from the 10 amp wire at point C? Yes, we haven't done this one yet at this distance, right? It's 4 pi times 10 to the minus 7 times 10 all over 2 pi. And now how far away is point C from the 10 amp wire? 0.3. When I did that, I got, here I'll write it this way, 0.66 times 10 to the minus 5 Teslas. All right, we'll get the direction in a second. And then the 20 amp wire. Have we done the 20 amp wire at 10 centimeters yet? Looks like we did, right? It was 4 times 10 to the minus 5. Okay, so at point C, 10 amp wire. Thumb is pointed to the right. And I wrap around the wire all the way down to point C. Which way are the fingers going? They're going into or negative K hat. And then for the 20 amp wire, thumb is pointed to the left. Fingers wrap around the wire, getting all the way around. And what direction are my fingers pointed as they come around the bottom? Outwards. So positive K hat. And I can put these two together. And it's 4 minus 0.66, so that's 3.33, isn't it? 10 minus 5 K hat Teslas. So what's the moral of the story when you've got multiple wires and you're trying to find the magnetic field? Do them separately. Find the magnitudes of their magnetic field separately. Get their directions, and then add them together as vectors. Yes. For the 20 amp? Which way are my fingers pointing? Out. Plus K hat. All right. We did a wire. Let's do a loop.
Please be zero.
Please. All right. I did say that we weren't going to do Bio-Savart anymore, right? I lied. You probably don't want to see any more derivations, right? That would not be good? Okay. All right, I'll spare you from the derivation. Let's do it this way instead. Okay. Let's deal with this for, I've got to make 2 of these. Give me a second. Okay. Let's talk, we'll do a square loop first. Okay. And which way do you want the current to flow? Clockwise or counterclockwise? Clockwise? Okay. You should know my 4A students have been, I've been giving my 4A students a lot of choices lately. I let them choose the color blocks that they got to use yesterday in their lab. And I got to let them choose something in lecture today. And I just let you guys choose the direction of the current here. Why did I do that? Yeah, because it doesn't matter. But I need to sell the illusion that you have choice. This class is not a democracy. It is a benevolent dictatorship, right? Always has been. Okay. Find the direction of the magnetic field at the center of this loop. Find the magnetic field, the direction of the magnetic field at the center of this loop. I should use O because that's what most books do. So how would you do this? You don't. So I see a lot of right hands out there. So how do you know what direction to put your thumb? Thumb goes direction of current, right? Okay. So can we break this up into 4 segments? Sure, right? So top segment, it's heading to the right. My thumb points to the right. And so as I wrap my hand around this wire segment and I get to the center, what direction are my fingers pointed? Inward, right? Okay, now we get to the right-hand side where the current is pointing down. What direction are your fingers pointed at the center? Inward. You get to the bottom segment. Inward. You get to the left segment. Inward. What's the answer? Inward. There's a quicker way to do that. It's still a hitchhiker, okay? It's like a corollary to the hitchhiker I just taught you, where instead of your thumb being the current, your fingers become the current. You wrap your fingers around in the direction the current flows, and your thumb tells you the direction at the center. Okay, why didn't I show you that first? All right.
I got the other way. My thumb is the same as everybody.
Oh, come back.
This is just
All right. Find the direction of the center of that loop. If I hadn't taught you the other way, what would you, right? Okay, right? But the direction of the magnetic field right here is not a dot. It's going to be inwards, right? And if I do current flowing this way, which way would the magnetic field point? Outward. So this right-hand rule for current loops gives you the direction at the center of the loop, right? Nowhere else. And the way that you distinguish these two things, okay, is with this following chart. So what I did is so many students over the years have had, there's too many right-hand rules. Okay, look, there are 3, okay? There's 3 right-hand rules, okay? And there's variations on a theme of these 3, but really there's 3. I say 2.5. But I'm a nerd. So, notice the big dividing line, okay, between the 2 different families of right-hand rules, right? What I call the handshake on one side and the hitchhiker on the other, okay? Handshakes involve what? Forces. If you are asked for the force on a charge, if you are asked for the force on a wire, if you are asked for the magnetic field and you are given the force, what kind of right-hand rule are you doing? You are doing a handshake from last chapter. Okay? That's how you know. And you can know 100%, right? If a force is being involved and you're looking for a field or a current or anything else, that's a handshake. Okay? And you'll do the handshake rule. And I've kind of listed, this will be on the PDF notes, okay? But I have listed, right, what different things do, right? I used the middle finger one because it was really the one picture I could get, okay, that made sense, okay? I believe these are my hands. I think I took pictures of my hands and then photoshopped out the background, okay? All right, so over on this side, hitchhikers. What's missing when you're using a hitchhiker? There's no force, right? I'm not sure I can be any clearer here. When are you using a hitchhiker? There's no force, right? If you being asked to find the direction of field and all you have is a current, That's a hitchhiker. Okay? The one thing I did not put up here was the magnetic dipole moment of a loop, because it's exactly the same as finding the direction of the magnetic field of the loop. You wrap your fingers around in the direction of the current. Gives you the direction of the magnetic dipole moment, which is also the direction of the magnetic field. Okay? So I didn't feel like it was necessary to put up here. However, there are two variants of the hitchhiker. And so how do we keep the two variants of the hitchhiker straight? Because it can be confusing. The answer is look at the shape of your thumb compared to the shape of your fingers. When you're doing the hitchhiker, your fingers are curled into your palm, right? Why do they curl into your palm? Because magnetic fields curl around wires, right? Notice that if you have a straight wire, the thumb is what? The current. Why is your thumb the current for a straight wire? Because your thumb is straight. Hold your thumb up. Thumbs up.
The hitchhiker thing? Yeah. Are you looking for this?
Stand it out. I need a. Hold yours up. Show everybody this thumb, this beautiful thumb right here. Hold that up. Hold it up high. Look at that thumb. This is called the hitchhiker thumb. Okay, do you see how it bends over a lot? Okay, you have the dominant gene. You had two dominant alleles that went in. That's the dominant gene expression. This is the recessive expression right here. Okay, I'm recessive in a lot of different ways. But do you see how straight my thumb is? Okay. If you have the hitchhiker thumb that does that, rah, okay, just pretend it's straight. Okay? I don't know, right? But do you see how your thumb is supposed to be like straight here and your fingers are curling around? If your wire is straight, your thumb is the current. And there's only one other thing that's left, and it's your magnetic field, right? But if your current loops around, right? Your current is now a loop. What do you use for the current? Your rotated looped fingers, right? And the magnetic field is straight through the center of the loop. I don't know how to communicate any more clearly that there is a distinct difference between the right-hand rules, the handshake and the hitchhiker. How do you know when you need to use a handshake? There's a force, right? There's a force involved. Or I should say probably more correctly, there's a cross product involved, right? Okay? Because the handshake is exclusively for cross products. Whereas the hitchhiker is a simplified version that's hiding some cross products. We didn't do the derivation, so you didn't get to see the cross product, but it's hiding in there, okay? And it works. And notice I divided this into two parts. You have straight wires where your current goes, your thumb goes in the direction of the current, and then you have wire loops or solenoids, which we'll get to later, right? Where you have wires that are wrapping around. And if your wires are wrapping around, you follow that with your curved fingers and magnetic fields your thumb. 100% probability.
So my explanation would be like hitchhiker.
Yeah. Yeah. Literally, when I ask you a conceptual question on the exam about the right-hand rule, you will pick an answer and then you can just say right-hand rule. Nope. Matter of fact, you can just put RHR. Right-hand rule, RHR. Okay? Now, this does bring up something about the grading of exams on this next unit. When I give you a conceptual question about the right-hand rule, right, and ask you to find the direction of a magnetic field or wire or whatever, okay, and you get it wrong, and your answer is RHR, how many points do I take off? All of them. Right? Like I can't save you, right? if you apply a right-hand rule incorrectly, right? Now, if your application of the right-hand rule was, say, one part of a problem, right? You're finding the magnetic fields of some wires or something like that, and I can see that, like, you're doing the problem right, but you did a right-hand rule wrong on one of the wires, I would have your back there and I would give you -1, right? Because I can see, like, you know what you're doing. It's just you applied a right-hand rule incorrectly. Maybe use the left-hand rule. I have to, like, be really diligent when you guys take this next test, because there's going to be several of you that are using your left hands. Get a tattoo or something, right? I don't know, but, like, I watch it happen. Right, left. But yeah, so I'll try to save you as much as I can, but if the question's conceptual and it's about the right-hand rule and you get it wrong, there's not much I can do to save you. So, yeah. There is a link on Canvas to a website. I was told that it's still working. That has like 40 or 50 questions that just, like, you can just click through and practice the right-hand rule. It'll tell you if you're right or wrong, but it'll give you a situation. You try the right-hand rule, right? So you might want to do that just to practice. Make yourself some flashcards. Do something where you are constantly reinforcing correct methods with the right-hand rules, right? Because they are, believe it or not, very important. Okay, let's do this. Okay, so I promised you I wouldn't do the derivation. But let me draw the picture. Oh, that was terrible. That was awful. That's not much better, but okay, we'll go. Okay, so we've seen this before, right? Right, where we had like a wire loop and we found the electric field at point P, that kind of stuff, right? We're going to find the magnetic field here. We would do this by breaking it up in a lot of little pieces. We'd have ds vectors. We'd have the Biot-Savart law. It would all go pear-shaped, right? If we weren't careful. We have an R vector right here, blah, 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 blah. Okay? So, after a miracle occurs, we would have found that the X component of the magnetic field, because all of these sideways components would do what? They'd cancel each other out due to symmetry, okay? And we'd only end up with these Bx components. It would turn out to be mu naught I, and I use capital R squared. That's the radius of the loop itself, okay? 2, and then an x squared plus capital R squared to the 3 halves. That's the magnitude, right? For a given distance away from a loop, right? That is the magnitude of the magnetic field along that axis. That's not as important as what happens if we apply this equation at the center of the loop. And if we're at the center of the loop, that means x is equal to 0. And if x is equal to 0, what does this equation turn into? No. Not undefined. That goes to 0. So we end up with an r squared to the 3 halves, which is r cubed. And then we have an r squared up here. And you can see how it kind of like quickly becomes that. That right there is the magnetic field of a circular loop of wire at its center. You could have this one in the back pocket, like for any loop, you know, you're on axis, if you ever needed to know that. I don't think I gave you any homework where you'd have to use that. But this is the more sort of applicable one, because we often want to know what the strength is at the very center of loops, because it's the center of loops where all of the interesting stuff is going to happen in a little bit. So that gives us the magnetic field at the center of a loop. Now, we also, when we did electric fields, we did arcs of wire. So let's say we had an arc of wire and we had current, say, flowing around like that. Okay. So the current comes in this side, arcs up, and then goes away. How much magnetic field will there be from these wires at this central point right here? 0. Because it's on axis. Do you see that? So the effective distance from the wire is like 0, and there's no magnetic field being contributed by these ends. So we don't have to worry about the ends at all. The only part that contributes any magnetic field at this origin point is that curve right there, that piece of arc. So if this is the only part that's creating magnetic field, it turns out that the magnetic field of that arc at that central point right here is mu naught I all over 4 pi r times theta, just flat, just times theta. And theta has to be in radians. So again, I skipped over quite a bit of derivation there, okay? But this is the general section of arc, right? So like for what I drew here, a quarter of a circle, what would you put in for theta? It's got to be in radians. Pi over 2, right? If it was a semicircle, what would you put in? Pi. You getting the idea? How do you find the direction of the magnetic field? It's a hitchhiker because there's no forces involved. But now you have a choice. Do you use your thumb or do you use your fingers as the current? So you can do fingers around in the direction of the current and your thumb would point in at the center, right? Okay. You can use your straight thumb and like follow it along the arc. It will give you the same answer. Okay. So it's just a choice. It's just that a lot of times this is faster. Okay. So that's what you do for arcs. And we can check it. If we have a full circle like we do up here, what do we put in for theta? 2 pi. And what's 2 pi divided by 4 pi? 2. Mu naught I over 2r. Is that what we have right there? And we just saved a whole bunch of calculus. Here you go. There's all the derivation in my very messy handwriting. So your eyeballs saw it even if you couldn't see it. All right. And I feel better. It does hurt a little bit as a physicist to not derive those things, but you know, it is a thing. Let's do a quiz. All right. Oh, there's more. Oh, yeah. Okay. And by the way, you have not met your full nemesis when it comes to the right-hand rules. Next chapter, there's going to be like 3 or 4, one after the other. No, 3 or 4 applications. No, there's 2.5 right-hand rules, but you have to apply them over and over again when we get to Faraday's law. All right. Let's do, so here's a wire with current that is flowing up. Sure. And here's another wire with current that's flowing down. Yeah, we'll leave those in black, okay? But this current will be red and this current will be blue, just to keep these wires apart from each other. All right. Will these 2 wires experience a force? Why? There are magnetic fields being generated by these wires, and those currents will be in those magnetic fields, right? So let's start with finding the force on the left-hand wire. So we're going to use the field from the right-hand wire to find the force on the left. So we got to figure out what direction the field is from the right-hand wire in the location of the left-hand wire. So how do I do that? Thumb is the current because it's a straight wire. Thumb is down. Over here on the right-hand wire, it's pointed into the screen, right? So that means that I've got magnetic field from the blue current that's pointed inward near the red current wire, right? Now find the direction of the force on that red wire. How do we do that? Current is going upwards, right? So I handshake upwards. How do I know I'm using a handshake? I'm asking for force, right? Field is into the screen. Which way is my thumb? It's pointed to the left. So the force ends up being to the left, right? Just doing the right hand rules right now. We're not going to do the calculations, okay? All right. Let's do the opposite, right? Same thing, but we're going to start with the red hand wire's field, right? What direction is the field from the red wire on the blue wire? Not on, but in the vicinity of the blue wire. It's also inward, isn't it? Okay. So applying the right hand rule gets me an inward, right? And now I apply my handshake, only instead of going up, I have to go down, fingers into the screen. My thumb is now pointing to the right, which means I have a force this way. What can you tell me about the magnitudes of those two forces? They should be the same. Why should they be the same? Currents are the same. Distance from each other is the same. So the magnitude of the magnetic fields are the same. And all that being the same means the forces will be the same. So what is the net force between these two wires? It looks like it's zero, isn't it? Okay. And what if we flip the direction, say, of the right-hand current? What if it was going up instead? It would flip the directions of both of those force vectors. And so instead of repelling each other, they would attract each other. So there's a force of repulsion or a force of attraction. And the force of repulsion and attraction depends on what? Direction. If they are going in the same direction, wires will attract. And if they're in opposite directions, what will they do? They'll repel. How many wires do you need in a cable to get power to go along them? I don't really have any good wires here today. The answer is 2. Sometimes a ground wire, okay? But the answer is 2. All right. What happens when the two wires have opposite current directions? Think about it. As we supply power to a device, current has to flow into the device and flow back out. What do the wires in all cables want to do? They want to get as far away from each other as possible. Okay? So I'm going to mention this now and I'm going to mention it again later. In networking, Ethernet cables, okay, there is a name for Ethernet cables that is very technical. Okay? They'll call them twisted pair cables. Inside of an Ethernet cable, there are 8 wires that are used to send signals up and down. Okay? And those 8 wires are in twisted pair. No, there's 10 wires. There's 5 twisted, 6, there's 12 wires because there's 6 pins. Anyway, right? 4 in it, I was thinking telephones. 4 in telephones, 6 in Ethernet. Okay? So there's 12 wires in there, but they form twisted pairs, right? Where the incoming and outgoing wires are twisted around each other, and you hook those up in pairs to the various directions that are going on in the plug. Why have they twisted them around each other? Wouldn't it be cheaper to just put the wires in the wire and be done with it? So they don't separate from each other. Okay? And for another reason that we'll get to later. Okay? But it's pretty handy to have those twisted pairs in there. You can get faster bandwidths that way. So I've just introduced to you the situation where we can apply forces to wires just by running current through them. Are we getting closer to a motor? All right. Without proof or derivation, because today's theme is we're not deriving anything. You know, can I be old for a second? No. The answer is no, but I'm going to do it anyway. It's a rhetorical question. 20 years ago, students would not let me get away with that. They would demand to know why. They would demand to know where it came from. I found over the years that with the internet, people will believe anything.
No, I want to know. I just don't want to be the outcast.
No, but like, oh, Mr. Balogh says it, then it must be true. No. You should dig into it. But okay, I am not a pathological liar, right? I tried to be honest and tell. That's not true. I am a pathological liar. I lie to you all the time. How do I lie to you all the time? Yeah, I don't tell you the whole truth. I leave out a lot of stuff. And why do I do that? It's been about 23 years since I last looked at it. And I can't remember any of it either. But also, there's a lot going on under the hood. All of this like, oh, friction, it doesn't matter.
No, but like, why though? I mean, why is so much cut out there? There's so much.
Baby steps. Why does it take 4 to 7 years to get a degree? Why not just download all of it directly into your brain?
I mean, like you're saying, over the years they've been like.
Do you know how many people would be in this room if I started this semester with the full vector, like curls and divergence and all that kind of stuff? 0. Yeah, no, it's bad. It's bad. We start off easy because we're teaching you problem solving. And then we layer on the hard stuff later. Well, you guys, I will never teach you hard stuff. That sounded bad. This stuff is very difficult. It's just in comparison with what I've done in my career, this is the easy stuff, right? But for you, I understand. It's very difficult. I get it. Okay, so without derivation, the force per unit length. Notice, I'm giving you this as a force per unit length. So it's like, this isn't the actual force. It's like the force over a meter or the force over a centimeter, right? It's a segment of wire. You can find the force on a segment of wire. Nope. Well, the derivation is, but what I'm giving you does not. I'll use D here. Okay, as the distance between the wires. Now, of course, if you know the force per unit length and you know you've got a meter of wire, you can find what the force is, right? You just take the right-hand side, multiply by L. Now we need to explain something to you that I mentioned was disturbing on Tuesday. Do you remember what was disturbing on Tuesday?
I don't remember Tuesday.
I choose not to remember Tuesday. Yeah.
Oh, the nitrogen.
No, you remembered the fun part.
Oh,
the,
not
oh,
not
the
this.
Henry's per meter?
Yeah, the Henry meters or the Henry's per meter, whatever it was. Right? We haven't gotten to Henry's yet. What's the 4 pi doing there?
Was it being too precise?
So all of these numbers, all of these constants, one of the things I've always been on you about, and if you give me a number that doesn't have a what on it, I tend to hand it back, is a unit, right? Units are so important, right? For making sure that we're communicating what a number means and all that sort of stuff. Where do units come from? So it's a measurement, but ultimately, where do units come from? They're a choice. We make them up, right? How do I know that this is about a meter? Because somebody said this was a meter, right? The original meter was 1/10,000,000th the distance between the equator and the North Pole of Earth on a line that runs through Paris, France. Very specific, because it was important to get because the Earth is different shapes and sizes depending on where you are. And so that's what they defined it as, right? Nowadays, we define it with the speed of light. Whatever distance light travels in 1/over the speed of light, time, is what we call a meter. It's about the same as 1/10,000,000th of the distance between the equator and the North Pole. But the point here is that a meter, a kilogram, a second, all of these things are standards that are a human invention to try to attach a label to a physical measurement in the universe, right? This setup that I've just showed you here is no different. If you take this setup and you set the distance between the wires to be 1 meter, and then you measure the force between these wires to be 2 times 10 to the minus 7 newtons per meter, which is very measurable with our technology. Actually, this was very measurable with the technology back in the 1800s. Then, so if these two conditions are met, then the current in the wire is defined to be 1 amp. So we've come this far in the semester. What are we in? Week 11, 12, 10 of infinity? I don't know how many weeks there are, right? We've come this far without letting you know where these units have come from. This is where it comes from. Because once you have an amp, you now have charges per second. And what are the units of charge? Coulombs. I never defined for you where that came from, right? I just said the unit of charge was a coulomb, and then we went on our merry way, right? All of these units, all of these numbers, all of these labels that we apply to them come down to a base choice, a setup. A piece of platinum rod about this long, we're going to call it a meter, or the distance that light travels in 1/over the speed of light. This is just an arbitrary choice that we then standardize to and pattern all the other measurements off of, right? What was the original kilogram? They literally put a piece of platinum iridium alloy and said, this is a kilogram. And then everything was standardized. Now, so it was only about 10 years ago that we redefined it according to something called the Planck constant. You don't need to worry about that. But like we tied it to instead of being an object that could lose its mass due to atoms falling off, we tied it to an actual constant physical. There are 26 fundamental constants of the universe. 26 numbers that tell us what? I think it's 26. It might be 27 or 24. There's a certain number of fundamental constants that dictate how our universe works, like the strength of the electric field. You know that one. What is it? Epsilon naught. The strength of the magnetic field. Mu naught, right? Those are fundamental constants, right? Sorry to let you know, big G is not a fundamental constant. What am I trying to say here? Why is mu naught 4 pi times 10 to the minus 7? We decided. Because we set that number to be 2. So the disturbing 4 pi is an artifact of our humanness, right? Of our choice of setting up these constants, and then all the other constants just fall into line and get direct measures. So there's the mystery. I'm sorry it wasn't more of an X-Files type thing, but you'll live.
All of, like, would it depend on our number system too? Like, we got like a base 3 system, right?
It'd be totally different. The number would be different, but the relationships would stay the same. Have a fantastic weekend. Practice your right hand rules.